ladies and gentlemen. It's my great pleasure to introduce our guest, Jörg Tiedemann from the University of Helsinki, and we will learn about the cross-lingual settings in Helsinki found in translation. The floor is yours.
Okay. Thank you very much. Thanks for inviting me. Thanks for coming here also during the summer weather. Good to see a full room of people. It's a pleasure to be in Prague, and I will talk about this title found in translation, basically a project that we're going to set up now. So we're still in the stage of setting up. So maybe you can expect a lot of results and interesting. About cross-lingual grounding, and I will also explain what I mean by that. And I will also show a lot of triangles, as you have one here already, a bit of a spoiler about what will be happening during that talk. Maybe that's related to when André Boyard came to Helsinki last year. He presented in his talk at some point, said that this was a talk with two to explain him. So let's go into that first part of the triangle here, and you probably have seen it a lot. So maybe usually I spend too much on motivating what I want to talk about. So if I'm getting too boring, please just indicate that somehow to me, and I can move on more quickly. But a little bit about language technology and artificial intelligence, because now people talk about artificial intelligence all the time. And I would like to argue, and maybe I don't have to argue for this kind of audience, that we are really in the middle of this core development of artificial intelligence, even though that people refer to AI for all kinds of things. And for me, I think when I present language technologies to students, I always try to also make an illustration connected to this triangle here. I'm just saying what we really want to do is that we have human languages that we try to focus on, but we want to build computational models that can handle languages in different ways. And then, of course, you can probably guess already what this triangle is going to be about. It's about these different components that are connected in applications of language technology as well. But I call these components now, so these components that really care about the essential things that we try to do in language technology, namely trying to find out how we can build models, computational models that can do similar to humans or in the same way as humans, doing some kind of understanding, so language understanding, trying to find out what is the meaning behind that input, this kind of language input that we have. And on the opposite side, that we want to do speaking or generating, writing, producing language. And these kind of two main components, core issues that we try to focus on are nicely illustrated by this triangle here, that we have some models that can take care of these different steps. And then, of course, internally we have lots of different smaller components that can build up on these two main things. I would also say that there's two different parts of looking at this, that we have these more kind of research-oriented questions about languages as such. So how do languages actually work in communication? How do they function? How does communication between humans work? So there's a lot of questions related to general linguistics here, of course, understanding the structure of languages and how they are built, evolving and changing over time. Then, of course, also these questions of communication and thinking and thoughts, and cognitive science comes into the picture, but maybe even philosophy. How do we communicate our thoughts by means of language? And then the more common thing that people, of course, think about if they talk about language technology is then the more applied side, that we want to build things that are related to interaction between humans and computers. So machines that can understand language and respond also to language, doing some kind of dialogue or interact in any ways, or maybe also mediate the communication between humans. And here I would say this is more related to practical computer science, applied computer science, and possibly data science, also a new term that is very often in the picture. So these two sides are really dominating the field, but they're quite different, of course, in essence. So either we look at more tools and applications, or we look at more basic academic research. Both of these sides, I would say, are really connecting also in the field of artificial intelligence, saying that we would like to model things that so machines or models that can handle languages in the same way as we humans do. And a big thing of, the big part of our intelligence is that we can communicate, we can use language as our channel of communicating what we want to reason about, what we want to interpret, what we discuss. So with this, I think we are really at the core of AI and should get more funding of this big portion of AI funding that is now floating around. But maybe, so you're not the audience that I have to convince, I should probably say that to other people. Then, of course, you realize also that this illustration is the typical triangle that is presented for machine translation, and that's also one of the fields that I'm mostly interested in. So if you put two different languages on each side and say you would like to understand one language and generate another language, this basically becomes the illustration of machine translation. And as you know, that somehow here in the middle you want to have some kind of model that performs this mapping from one language to another. Maybe not going the full way of perfectly understanding or speaking another language, but trying to approximate it in some way. So, looking at today's or the current models that we have, so now we have a dominating field of deep learning and neural models that dominate the field. And a typical situation is that we have neural machine translation in the setup of some encoder-decoder setup. So that we have two different steps or two different parts of a network that tries to do some kind of encoding of symbolic representations of language text, for example, or some other kind of input, and tries to then abstract that into some currently vector, so some vector-based representation, some representation that is learned in the training phase. So how you can map from one language to some internal representation. And then we have a decoding phase that then produces the language. So this nicely also fits into that triangle, of course, because the encoder somehow tries to approximate the understanding part, whereas the decoder then approximates the generation part. So in that sense, this becomes really interesting because here we have all these aspects of language technology integrated in this network, and we would like to see what happens inside of a network. So this is the interesting part that we would like to investigate from a research point of view. What kind of things can be learned and how are language items represented in such a model. So even more triangles. So if you now think, I wasn't really sure about that picture, but I threw it in the end. So there's also, of course, a triangle that tries to explain meaning representations or try to see the connections between reference in the real world and thoughts and concepts or symbolic knowledge. And we can think that also this actually fits into this picture quite well. If we have symbolic representations here in source language and target language, they refer to some thoughts and concepts, so they're close to the meaning that we want to convey in our messages. But they also refer to some real-world items, so that there might be some referent that they refer to. And we can think of that these things are kind of hidden here, so the referent is somehow hidden in the model, but both languages try to refer to that with their terms that they use. So somehow concept and reference should match in the setup of bilingual models here, or translation models, because we would like to preserve some mutual understanding, so we can assume that we have the same thoughts and concepts that we refer to when translating, and that they also refer to the same referent. So you could think that the model itself somehow, now we come to these terms of grounding. If we talk about grounding, we usually try to refer to the relation between the symbols and the referent in the real world. This kind of hidden referent that we don't see is somehow indirectly grounded by looking also at the target language, because they refer to the same thing, but they are grounded not exactly by the item in the real world, but instead with some representation in another language. And this is what we want to make use of, and I explain later a bit more about this. And the idea about the project that I'm trying to present here today is that if we have more of this kind of evidence that we can get from different languages, so if we get a lot of different language input, then we get more of this indirect relation between symbols and some references in the real world, and also to the concepts that we try to convey. So having this kind of illustration, this is basically the setup that we try to explore. How can we somehow find different internal relations that are not there, but in a neural way. So coming to language grounding, so just once again, so what we otherwise would refer to that in some pictures that explain this well. For example, if we have here a sentence, a wall divided the city, and we have a picture here, the image, then we can very quickly disambiguate the term wall, because it refers to some visual element here in the picture here. So we can see that this is the wall dividing the city, so a solid wall built inside of the city. And if we have now translations, then we can also see that in translation, the ambiguity of that term here will be disambiguated, so it will be resolved by looking at the translation, which then indirectly is the grounding that we also have in the picture here. So again, this is still my motivational part here. I think it's probably not that much to discuss about this, but I think this is a quite nice setup for exploring multilingual data sets. So before coming to the real topic where I want to present really sentences or longer utterances, how they can be explained, or representations for longer utterances can be learned, I would like to go back to some prior work that we have done. This is more about lexical items. So again, similar to what we had in the examples in the beginning, that we can resolve certain ambiguities on a lexical level. And I will just give some quick examples, go rather quickly through that, and then come later to the sentence representations that I want to talk about. So the idea is really to use bytext or bilingual parallel text as some kind of semantic mirror. And this idea has been proposed by many people, and especially the semantic mirror term has been coined by Helge Duvek in Bergen, who used that for discovering word senses. So I will also have this example here again. So we can use translations now, some kind of implicit supervision for getting information that we have not explicitly in the data. So in some sense, we treat translations as annotation. Annotation is also just a language on top of the original string, and now we have a translation that is now the annotation that comes naturally from humans. So it's not really designed to annotate, but it preserves the same semantics, and you can think of this as just another language explaining what is going on. And then we can see what kind of distributional patterns happen between languages, and that can be a nice signal for us to explore. So first, these examples on lexical semantics, where we can look at word senses, for example, and different semantic relations. For example, synonymy could be something that we look at, but also one example where we can look at the identification of idiomatic expressions. So this is an illustration that somehow visualizes what we make use of here. Languages are so different, and these differences are exactly this interesting signal that we want to explore here, because they don't have the same ambiguities, the same kind of representations. So coming back to this semantic mirror method, so that is proposed by Helge Duvek in 1998, or maybe even earlier, I don't know exactly. But the idea is here to have really just a set theoretic method of going back and forth between lexical translations in different languages. So he had proposed the idea that we can look at the translations of individual words, and from that we can discover certain clusters of meaning of a word that is ambiguous. For example, the Norwegian tak here, that can have different kinds of meanings. It's actually also a bit of different word classes. But if you then look at translations into English and then going back again, then we can see that some clusters or some groupings appear out of the data, just by not even using any kind of frequencies, but just pure set theoretic combinations here. So that we have the sense 1, that is more like a roof or ceiling sense, so the roof sense of tak. Then we can have something that is more related to a cover, so something covering something else. And then we have also actually the verb to hold I'm not exactly sure about Norwegian. I should know more about Norwegian, but so we have the sense of taking something, gripping something. So playing around with this and also going back and forth several ways, this gives us some way of dividing the lexical item into different senses just by looking at how it is translated. Then yet another example is that you can also use translations for discovering synonyms. And this goes back to the distributional similarity methods that we are all used to, so that we have somehow we can define the use or the meaning of a word by the company it keeps. So these famous quotes that we know from distributional similarity. So looking at the context, we know what this word is denoting or what it kind of refers to. Another thing is that we want to not use the monolingual data as the context, but we can at the same time, or in combination with the monolingual context, we can also use translations as a context. And we can find items that share the same translations. And that also, of course, indicates something about the meaning of those words. So this is also something that we used in some experiments, so that we can, in a typical way, try to build some context vectors with frequencies, but just not looking at the context in the same language, but instead using automatically extracted translations from word alignment, for example, across many languages in parallel. So if we then have these kind of vectorial representations, we can do the same things as always, that we have some kind of similarity measure, and we can figure out whether certain words have the same distributional patterns across all these languages and make some conclusions from that. So for example, here for the Dutch items lente and voorjaar, we can then conclude that these vectors are very similar with all these aligned words in different languages, that we can conclude that they're most probably synonyms, whereas other things are not in the same relation. By the way, you can ask questions or make comments at any point. I think that's fine with me, if that's fine with the recordings. But this is really just introductory parts here anyway. So, one other thing that also I found very interesting is that we worked on idiomatic expressions, and this is something that uses some different kind of signal across languages. So if you think about idiomatic expressions, that are expressions that are somehow fixed to some degree and don't have a compositional meaning. So the assumption and approach that we have here is that if you look across languages, especially many different languages, then we can measure this kind of non-compositionality. So we assume that these translations are much less predictable, because now we have an expression that as a whole represents something different than the components that it is made of. So somehow we can measure this kind of predictability in translation, and especially also we can measure the non-compositionality by looking at how these individual components are translated, and then compare that with what we actually see in the translation. So I found that quite interesting, especially because this uses the fact that, for example, if word alignment goes wrong and wild somehow, then this is a good indication that this is probably a more complex expression that we should look at. So that's also what we did for Dutch, and we focused on support verb constructions and looked then at automatic alignments to make some conclusions on whether some candidates that we could extract from the data, whether they could indicate some idiomaticity, so some kind of connection that is beyond just pure compositional usages of words. So we extracted some support verb constructions, also did morphological analysis and all these things, and then looked at the translations, how they are translated. And by using some simple measures, like for example, some translational entropy measure, that is here the column which we sorted on, or this is another measure that we defined. This is basically the proportion of default or the default translations that we have per component in the things, in the items that we observe. So if we use those measures here to rank our candidates, this became a very nicely ranked list of idiomatic expressions, where the most important or most idiomatic items or expressions came up in the top, whereas other things really moved down in the list, and we had a nice reordering of these candidates here. And this was in combination with some lexicographers, and they were really happy because that's really difficult to find idiomatic expressions that you should include in a dictionary, for example, in a lexicon. So this was also, again, one thing that we could use the signal from some parallel corpus to indicate some semantic effects going on in the source language. Okay, so with that, I would like to move on to larger items, so going to sentence representations and some more current stuff. So now I'm moving really towards the ideas of this new project, and as I said, a lot of things are still very preliminary and really setting up the whole project, so I will only represent some initial experiments. But I think we have already a lot of interesting and encouraging results here, and I will present them just in a minute. So, but sentence representation learning, we know about representation learning now. It's really the most popular thing to talk about. Trying to get some mapping from, for example, individual words to some vector-based representation. We would also like to do the same for a whole sentence, mapping that to some kind of abstract representation in some vector space. And one of the tasks for testing that, is that really working? Can we do that? Getting some semantic abstraction in this representation level. Then we can look at predefined tasks where we have some data for testing them. And for example, tasks that are set up for measuring how we can make inferences between different examples of sentences that we know have a certain relationship between each other. So of course the idea is that we would like to see whether a system can do similar kinds of complex reasoning over natural language input as humans do, if the machine can do that as well. So these sets are quite simple and straightforward. Typically they have just three relations, so they have some kind of contradiction, entailment, or neutral relations. And then if you have sentences like those that are taken from the Stanford corpus or natural language inference, the machine basically has to do something that is simple classification, just given two sentences. It has to decide whether a certain logical relation holds between these sentences. And as you see here in these examples, most of these examples try to focus on some complex reasoning that you have to do, so that you have to really understand what is going on. It's not really simple word matching that you can perform to solve that task, but instead you have to do some kind of reasoning over those sentences, so that to analyze those sentences saying that they contradict each other, you have to have some understanding about what is going on in those sentences. So there's plenty of these examples. That's nice. Now people work on building these resources, especially for testing, so that we can build methods and systems that can measure these kind of behavior, whether systems can really learn these kind of logical relations. Now doing this with sentence embeddings or sentence representations, here's one setup that we have worked on, and that is also very common in the literature. So now if you have training data that you can train systems on, where you can learn a sentence embedding some kind of semantic representation of a sentence, then you can throw that into a classifier, basically also here a neural network classifier that can learn in a supervised way using those representations to make the decision whether this is entailment, contradiction, or neutral. So you hope that here you have enough semantic information in both of these sentences that you can throw it into some classifier that can really make use of the information that is here accumulated to make a decision in these three different classes: entailment, contradiction, and neutral. So one sentence is then called the premise, and the other is the hypothesis, and then you would like to find the logical relation between them. And this goes basically in this fully connected classifier that we have here. And as you can see, there's a lot of black magic already here, because it just tries to do different kinds of combinations of these vectorial representations. Because it works better, there's not a good explanation why this is now a good way to doing it. So here's a concatenation, this is kind of element-wise difference, and this is a element-wise, well, the dot product basically between those vectors. And because they kind of combine in different ways, that works better than having just a concatenation or some single version of combining them. There might be some other ways. So this is kind of the things that we don't like throwing in. Experimenting really shows some effect without us knowing why this is happening. So this is the actual architecture, and as you can see, there's even more of this black magic that is difficult to explain. But now, I think the reason for showing this is not only to impress that we can make these kind of diagrams, but it's actually a student from us, so my PhD student who made that diagram. So he experimented with lots of different architectures, and this is the one that worked best for him. So there's not much to say why this is really the case, but we have, in the same way as for machine translation, it seems to be beneficial to have several layers of abstraction here. So this looks very much similar to, for example, the encoder layers that we have in machine translation, where we have different layers of recurrent networks, like these bidirectional RNNs here in the 3 different steps here. And they capture different aspects. What exactly is difficult to say. But they learn different things that seem to contribute to the whole picture here. So we have recurrent networks here that go through the input sentence. So this is the sequence of words. And then we have in both directions some kind of hidden layers that learn some representations. Then we have another weird thing, just a max pooling layer on top of that, meaning that we take the maximum of each element of those vectors that come out of here. I still don't really know why that is really a good thing, but it seems to work. And we do that on these 3 different levels here, that these recurrent levels are initialized in different ways from the previous layer here. And then concatenating all these max pooled values here come into the classifier that we then finally train for this entailment detection. So this is something that really works in a supervised way. So you throw this into the supervised classifier training procedures, and it learns surprisingly well to make the decision between these different candidates that we have in a test set. So if you have now some common test sets, like the Stanford NLI data set that you can compare your approach to others, then this hierarchical max pooling approach that we have here is, at the moment at least, until ACL, I think, it's still the state of the art of this kind of approach here. So you can see that we have an accuracy of 86.5%, and I think for this very difficult reasoning task, this is something that I wouldn't have expected just out of the box from implementing this neural classifier here. You can also see that here, and some more details, that this really, compared to similar setups, like this is very similar as the setup that we have here. We have a clear improvement on all these different categories. So contradiction and entailment, really close to 90% accuracy by that model. And not really surprisingly, the neutral class is the most difficult class, and that's also something that I think for me is quite natural, because it's very difficult to say that something is neutral or has some kind of entailment or contradiction in there. So also systems, I guess similar to humans, make some mistakes here. And this is also reflected by this confusion matrix here, so that we have in the neutral cases some deviation that is bigger than for other classes. So now why would I show this? So this is, of course, something that is really monolingual. So we have some training data where we learn some sentence representation, and then we do the classification for entailment detection. But now in our project, we have that idea that we would like to improve that sentence representation. Now this is really learned just in a normal way as kind of a monolingual language model. But here really the idea is that can we make use of this structure, this setup that we had in the beginning, that we also learn representations from the signal that we get from a target language. So we have multilingual settings, and we have that signal of the target language as well to somehow find some abstraction that represents a sentence, which will be produced by this encoder model here. So the question is, what kind of abstractions does a model learn if it has to learn how to translate? So if it has to learn to translate, we hope that we assume that it really has to do some abstraction, some kind of understanding to make a proper translation. So it would be a natural idea to see whether this kind of abstraction that we get from machine translation gets into some direction that is much more abstract on a semantic level than just purely looking at monolingual data. So the idea is that in this project specifically is that we want to go away from just bilingual settings, so only having one language and another target language that we translate to, but instead, if we now assume that we have access to quite a lot of diverse material from different languages, so making the task harder for the machine translation system, would then force the system to have less of the possibility to make shortcuts between two languages. Because languages can have a lot of similarities, so then it doesn't really have to do a lot of understanding. We know from the success of statistical MT, this works quite well, just purely matching over from one language to another. But instead having lots of languages and having one model that has to cover all these languages, we assume that a system has to do a much stronger abstraction to some higher level of understanding to actually match to all these other languages as well. So that's the assumption here, that we have some kind of interaction between all these languages and the diversity that we have, all these source and target languages, and because they have to be integrated in this system here, we hope that the abstraction level really goes up and that we reach something that is much closer to some meaning representation than just a bilingual model. Does it make sense? So whether that works is a different question, and that's a question that we have some money for now. So this is this kind of found in translation. So finally we come to the project that we try to set up. So this is now a project where we try to set up experiments, of course, and then also some kind of questions about how to make the architectures to work, that we can find out whether this idea that intuitively works nicely really does something useful in a practical setting. So we have now, so that project will officially start in September, and we have 5 years in finding out, and after that, well, I can tell you more. But I want to tell you at least something here, and I think I probably would not have received any money if I would not have any kind of pilot study, at least convincing that something works. So we had at least tested whether multilingual systems do something interesting here, and that's the remaining part of my talk. So we trained translation models, basically multilingual models, and we used English as some kind of pivot language here. So saying that we take translations to English and from English as our training material. We train some kind of neural translation model, which has this kind of encoder, decoder setup and with some attention. So it's a very basic traditional, well, not traditional, it's a basic setup of today's neural machine translation systems, even though they evolve very quickly. So this is very simplified as a picture here. We trained this multilingual machine translation model and basically used something that has been proposed before, so using some language flags to indicate what kind of language we want to produce in the output. But now, instead of really being interested in the translation model here, we want to use that to test whether we get some kind of paraphrase model between English and English. So note here that we never train on any English to English text here, but also only train on English to other languages. So what we assume here is that the encoder somehow learns to encode English into some abstract way, some abstract representation. And then also, because we have the opposite direction of the training data here, we also assume that the decoder can really speak or generate English as the output, and using some kind of abstract representation that some encoder will produce. So we never train on English, but we will nevertheless try to see whether that model can be used as a paraphrase model. And the idea is, of course, that if that really happens, that really works, then we can at least prove that something interesting is learned by the system here. So we try to test this kind of cross-lingual grounding here, now with the hypothesis that if we increase the linguistic diversity, so some different kind of training material that we put into the system, can that really increase that abstraction that we observe? So here again, saying that individual models could be much lower in the abstraction level, whereas we hope that we get some more higher abstraction with the multilingual model. So we use Bible translation here. Bible translations mainly because we wanted to have a large variety of languages that we can throw in. So there we have up to 1,000 languages involved here in this corpus collection. So we can actually experiment with lots of different languages. So what we did is we just used English-French as one of the examples of the standard example of training some translation engine. And then we had a model that only trains on all English Bibles aligned to one single French translation, to having the minimum of translations as the output that we can imagine, but still having all English Bibles here. Then we have a model with all the French translations, so we get more variation, and we hope that this variation somehow gives us more abstraction possibilities. And then we throw in additional auxiliary languages and see what happens. So I skipped this here because this is just the numbers of the training data. So this is the training data that we have. There's maybe some interesting things that for German, for example, you also have a lot of alternatives. Some other languages have only one, others have a few Bible translations. They differ quite a lot from each other, as you can imagine. Also historical variants are in here. And then as a test data set, we used actually something that is now out of domain. I also wanted to see how much that can get out of the Bible domain here, because we don't want to just specifically train something for this very domain-specific language domain that we have. So I took data from this Tatoba data set that I have, that is online available, and we can get these kind of alternatives that people have just uploaded as some alternative translations of certain phrases and sentences. So I used those sentences here for testing, and the main idea is that can this model then recognize paraphrases, mainly saying that how surprised is the model by seeing these paraphrase examples here. Measuring that with entropy, seeing that what is the entropy of the model seeing a paraphrase sentence. And this is what happens. So this is now with the Helsinki NMT system that we have, some preliminary results where we trained the systems with mostly comparable setups. So of course there's variation. It's quite difficult to have completely comparable training procedures. With this single French translation, but still the complete English data set, we have quite a high complexity here. So of course, what does this number really refer to? I mean, it's difficult to say what over 200 in perplexity means here in that case. But you can see that the reduction in perplexity is quite big already when you just throw in the French translations that we also have in the collection here. So this is really a dramatic reduction that we can see here, which already shows that some variation gives a better abstraction for the English-to-English task. So this is still English-to-English, right? And then throwing in some other languages, we can see that it not always really works, but in most cases, we really have a reduction that goes beyond these English-French perplexity that we can measure with the English-French Bibles here. And we go to something that comes quite close to the supervised model, which I call supervised here now because this is straight on English and English Bible variants. So training really for seeing different paraphrases of English, whereas the others never see any English data in training. So I think this is very convincing to me to say that this is encouraging enough to really say we should explore this further. For completeness, how much time do I have actually? Still enough time. For completeness, also the translation scores. If you look at French and English French translation, so if we are in domain, then this is the kind of baseline that we have for training on English and French actually in both directions in one model with all English and French Bibles. And we get these kind of bleu scores here. And then throwing in some other languages, we can see that in many cases we get some improvement here. It's not consistent. And it's only bleu scores, so no very careful evaluation of what happens here. But we can see that throwing in some other languages really gives us some improvement here, which could also indicate that we have a better abstraction level. Well, it's a bit difficult to make that conclusion. But still, we can see some improvements for most of the languages, which seems to indicate that these other auxiliary languages really help for some weird reason. I think more interesting is the out-of-domain case. So if we go to some other domain like the Tatoeba, so now we test also for French-English and English-French, then we can see a slightly more pronounced improvement of the scores that we can get. Now the scores are much lower because this is really trained on Bible text and Tatoeba is completely different, so it's very much out of domain. So these baseline scores here, 17 and 13, are really quite low, so maybe not that trustable. But we can see that throwing in some other languages seem to push the model into some abstraction level that seems to go away from very domain-specific knowledge that we learn, but instead getting some more semantic abstraction, hopefully. Yes?
For example, does it mean that, for example, the Swedish line, if it includes English, French plus French plus all the other?
Okay, yeah, no, good question. I should have said that it's only always just one language added. So all of these take English, French, and then add those languages. They're not accumulated, no. We have also models with all these languages involved, but then basically the system breaks. It doesn't really work well anymore. So it's only one language added. So we have more time to test other things. So hopefully we can see similar patterns with more languages involved. So just also to show some learning curves, and now you have to observe that this is actually a different experiment. We reran that with Marianne NMT, also to get more closer to some kind of convergence that we can get. HNMT somehow didn't give us the performance anymore, so this is kind of an outdated system by now. We moved on. So this is kind of the Marianne NMT experiment, where you can see that if we have only English-French as the training data English-French, and on a validation set, it really learns that quite well, the English-French translation. So validation goes really down as expected. It converges at some point. But then if we measure for the same models that we save here at these different save points, if we measure the English-to-English paraphrase perplexity from our test set, we can see that this really fluctuates quite a lot, and then in the end actually goes up even. So it seems it's a typical picture of overfittings, really overfits more to the translation of English-French Bible texts. Whereas now if we throw in Afrikaans as just the first language in our list, so no big reason for that otherwise, we can see that it actually follows the same convergence line here. Now we have another language that it has to learn during the kind of translation process. So validation curve is the blue line here again for English-French. But if we test now on our test data for English-English paraphrase perplexity, then we can see that it also goes down until the end. It basically converges in the same way. So this is quite nice to observe. And this is consistent for all the languages that we have. And this is now a model that includes all languages. And we can see that actually the perplexity is much lower than before. So the scales were different. So now this becomes the lowest perplexity that we have seen for English-English paraphrases. So I hope this kind of also makes it convincing for you. We have something else that maybe can be more quick on that. So if you also want to generate paraphrases, so of course you can also not translate into different languages, but you can actually generate English from English input. The thing is, because we don't include English to English, it doesn't learn to produce the identical sentence. What really happens is that we have very rarely the same sentence coming out of the translation. So it seems to be on some other level decoding into something else. Whereas if we include English-English here, then we can see that the system, because it sees a lot of identical sentences, the most obvious thing to do for the model is to produce the identical sentence. Whereas these other models seem to learn to produce some other alternatives. Now, here's no clear pattern here, so there's nothing really to see. Now, I think I skipped those pictures here because they don't really say much, so I skipped them. If you want to ask something about that later, you can do it. Here are some examples, and there maybe just cherry-picked some things to entertain you. So this is for the, not entertaining, but showing some examples from the Bible. I think they make somehow sense. So if you have the source coming in here, it's actually verses, not sentences. And then you can see what kind of paraphrases the system produces if you generate from English input. Some are better, some are worse. So you can see that it does variation at least. Give attention to this, pay attention to this. Sometimes it's a very small thing, sometimes it really does some bigger changes here. This is kind of difficult to evaluate, so how do you evaluate that? That was the picture that I skipped about you can measure blur, but it doesn't really, because blur would be optimal if you match exactly the reference. Well, it's not really what you expect from paraphrase detection, and then you have these other measures that measure how different it is from the reference, but it's very easy to generate something that is very different, but it's completely wrong. So I don't really, it's difficult to evaluate that. So now more difficult is also to do that on out-of-domain data. So if we have Tatoeba and we have trained now on Bible text, you can see what happens. And this is maybe a bit more for entertainment here. It's a bit cherry-picking again, but so you have some examples like, well, kiwi replaced by grapes is maybe okay, but cell phone probably was not in the Bible. Replaced with a scorpion. Somehow French was maybe not mentioned that much, but that was changed to Greek, but I especially like this one here. Could I park my car here? Do I get up here with my cavalry? maybe a good example of something that is paraphrased in a biblical way in some way. And here you can see some weird things that come out as well. So you can see that this what happens in the baseline model. It actually doesn't learn to produce English from English input, but it still produces a lot of French. So it doesn't really learn that mapping, whereas with other languages, it really produces at least English, and then some things can happen, I don't know. The flying creatures shall fly away. I mean, that's also quite nice to this birds fly thing. But again, this is more cherry picking than anything else. Okay. I can quickly also show something else that comes out of this. So if we have the same setup here, and now we want to, what did I have? Yeah. So if you want to have the same setup, but now test with more languages. So first picture, I can very quickly show that if you want to test this for translation, and then people talk about zero-shot translation, for example, with language pairs that you have not in your training data, it basically fails. So it doesn't really work. And I think you had in the morning, there was a presentation about that blur scores can go down, but some other measures go up. So there's not a really correlation between necessarily. So we have all of these black numbers here are zero-shot translations between language pairs. It doesn't see in training, and the scores are ridiculously low for that setup where we have only 42 languages involved in the training procedures. But the more interesting part is actually this kind of language flag here. So now we force the system to learn translating between all these languages, and the model now needs to compress all that information into one network. So now the system really has to do a very strong compression. And the way of how to do this is, of course, if it can reuse things from languages that are very close to each other. So it learns to reuse these parameters because it has a common parameter space. It learns what kind of parameter subspaces it can reuse, what kind of languages it should put close to each other to use that information with the same parameter space that we have here. So this language flag here triggers the languages that we will create. So somehow here, this also triggers how much of the parameter space can be reused by the system. So what means that this kind of language embedding that we get from this language flag here really indicates relationship between languages, at least in the task of translation here. So what happens here, so I just give a little bit of pictures here. In the beginning, it's chaotic. So after some training, it's just a mess of different languages. Now we have these 42 languages, I think, again. And then it reorganizes things. So this is now plotted on 2 dimensions. And you can see that, of course, it's not perfect, but you can see some clusters coming up, like some Romance languages clustering together, some Slavic languages. There's some weird things going on. I think the most funny thing is that we can probably see that English is really a weird language. It's kind of an outlier from the beginning, but it borrows a lot of things from other languages, so maybe that's not so surprising. So what happens is that you get some clustering of languages, and I think this is really interesting because it comes purely out of the data. There's no information about these families and relationships between different languages here. So this is now done for 42 languages. I also did that for 972 languages here. The restriction here was to have some vocabulary that we could still manage to have in memory. So some languages fall out of the set here. But we can see that after training this gigantic model with all these languages involved here, the translation does not work at all, but it picks up very nice clusters of language families here. So here it only illustrates the 10 language families that have most examples or most languages in the data set. And we can see, of course, that this is not perfect. This is also, of course, a reduction on 2 dimensions now. But we can see that it's definitely not random here. And it tries to put things together where they have some stronger relationships between each other. So, of course, now this is a starting point. So I would like to see what can we do with this kind of visualization here. Does that really reveal some interesting relationships between languages that we wouldn't think of otherwise? So there would be a nice, interesting direction also to go into some typological questions, whether we can see, does that come out of the data, what we expect from languages? Does that discover something new that we haven't thought about? So that's basically where we are. So just to summarize, a bit more advertisement for the project. So this is what we set it up like. We would like to have sub-projects that are focused on modeling and architectures to see what kind of models and architectures work best for this setup here. And then we have something that many people jump on now, so the kind of interpretation of these models and these learned patterns that we see here. So how can we intrinsically interpret what comes out of the networks? But then also 2 extrinsic or task-oriented evaluations. We want to look at what I presented in the beginning, this kind of natural language inference, semantic reasoning. So how can we use the representations that we learn from these models here to do some interesting human-like reasoning, some kind of reasoning that approaches human understanding. So this is this NLI part, and here we also want to check whether the system can also improve multilingual machine translation. And of course, the idea is that somehow can we see something emerging out of the data that really is not an interlingual really, but some semantic interpretation that is more or less language independent across all these different languages. So this is then something that we would like to test in a translation task, whether, for example, some small low-resource languages could also make use of these kind of emerging representations that come out of multilingual models. And then, of course, the typical part that we would like to publish as much as possible about that and having some workshops. So maybe you can see, hopefully, more about that. But those things that come out, also data sets and possibly software and workshops. So, to summarize my ideas here, and then this is more like advertisement again. So this is something that I show to funding agencies. We would like to stay in this triangle here, of course, work with multilingual machine translation, and we have different complexity of the task of the goals, the more risky goals on the top. We would like to learn these semantic representations and interpret them. We would like to see if there's some continuous meaning space of languages that we can see, so some kind of semantic space that emerges. Or can we go to human-like language understanding? We will see how much we can approach with our ideas to go to this goal of finding better better abstractions to get closer to language understanding. So we have a website about that as well. There's not that much yet, but you can hopefully follow that if you want to know more about that project. We have a growing group together. This is just a snapshot from one of these discussion groups. They didn't know that I'd take a picture. Some realized that I was putting my phone up. But yeah, so hopefully we will have more coming out of this project in the near future. And well, I hope I can present something else in some other time. So with this, I'm basically done. Thank you for listening, and open for questions.
Thank you very much for your extremely interesting talk. So we have some space for questions. Are there any? Yeah.
Maybe just a quick question. I've been wondering how much does the outputs get screwed by the data source, namely the Bible. So I've been wondering if you've tested the system on some other much contemporary data, like European Parliament sessions or stuff. I know it's difficult to find some parallel corpora, but still.
Yeah. So we have not really done that yet. We would like to do that, especially also so one thing is we would like to go really multilingual, and there's not such a big choice of different data sets that you can use. One idea is we would really like to go beyond 20 languages or something like that. So we would like to have hundreds of languages, and then we are restricted to religious text, for example. But I think one interesting question is how can that multilinguality be combined with bigger and more contemporary data sets to see whether those different complementary data sets can push that model into some other directions as well. So not only variation across languages, but also variation across domains could be interesting, I guess. We haven't really done that, so no results for that yet. We have done some multilingual models for now WMT, and they don't really work for some reason, but well, yeah.
Thanks.
Okay, so you mentioned at the very end that one of the goals is also to interpret the models. But you know, during the talk you talk about inferencing and paraphrases and so on. So could you just have some thoughts, because I think that's a very hard problem, sort of on top of everything else.
I thought I could get some input from you, because I'm also very puzzled about how to do that. So we have no clear idea about this besides our visualization. Like in the end, we have some visualizations that we can do. This is already nice. We can see that the language flags, for example, indicate some language space that maybe makes sense. We also did this kind of clustering of languages with hierarchical clustering. It's not really internal. Well, it's more looking at the internals at least, but we don't really have a good idea on how to visualize, how to really interpret the different parts of a network. So one thing that I would like to do is to, for example, do some more forced training, forcing certain parts of the network to do certain things. So setting up multitask training procedures where one layer probably looks more at syntax and some others more and then some other features, and to see whether that really stays in that layer after training procedures continue, and that reveals maybe some subgroups that you haven't in the initial setup. I don't know yet. So I don't really know exactly. So I really hope that I get some more inspiration, and also from discussions with others that we know how that can be done. So far, I only think about some things like manipulating, for example, the input sentence by some known change, taking away negation, and see what happens inside of the network, and see what kind of parts of the network really take away that information or not. So manipulating input and output might be a way to see what happens internally in the network. Whether that really comes out naturally, I don't know. That's one idea. Would you have any other idea? What would you do? What do you do here?
Well, if I may, follow-up question. So I don't have a suggestion, but just a general direction maybe, because that's how we are trying to write our proposal that we discussed. So do you see any place for, let's say, a symbolic representation, close to your meaning on the top of the triangle, which would maybe go further than current representations, maybe to some logical representation like glue semantics or MRS or something, on which you can, for example, do inferencing, because people do these things exactly because they want to do things like inferencing. And then those things, of course, can provide explanation, because you have the proof, from the two sentences with some conclusion, and that obviously is the explanation. But I don't know how to do it. But do you think that could be one of the ways to try to relate the distributional model with the with the logical proofs, so to speak?
I also don't know how to do that, but it would be interesting to see, of course, whether that kind of distributional representation that you get out of here would match with something that, from expert knowledge, would be a good representation in a logical way, for example. So I could imagine that maybe some relationships can be found by, for example, attention mechanisms, and that can be reflected by logical operations, for example. So I think that would be a way of seeing whether those individual relations come out of the network somehow, somewhere, and whether that could be explained by, for example, a symbolic representation that someone also would put on the same data set or the same input. And in that way, maybe bootstrapping something that this kind of mapping between continuous representations and more discrete ones could be found in the data. I don't know if that somehow answers the question. It's really a difficult question to answer. I think I don't see an immediate way of how to combine those. There might be something coming up in the near future, because many people work on that interpretation question at least. But so far I don't really see at least a good mapping from one to another or integration as such. But I think looking at relations that are learned from a system and then seeing whether that also can be explained in a symbolic way would be an interesting way to go. Would it?
Okay,
yeah.
Thank you.
For example, what we also try to look at now is, I think also many people do that, what does attention really represent? So now if you look at, for example, syntactic information, does attention reflect syntactic relationships somewhere in the network? So that is, of course, not really the semantics that we are looking at, but there are some other things that we have quite well established frameworks for. So we can easily match whether the system learns these kind of structures from data, and I think that could be a way of checking whether that really makes sense also from our expert knowledge point of view.
Okay, let me ask some question too. When you speak about the hundreds of languages, it's obviously extremely computationally demanding and also resource demanding. So would it be possible to simplify that and to choose just the most salient representative out of each language group, or, well, if we measure some kind of language distance, then choose just the centroids of the clusters, or try to reduce the computational.
Yeah, that's definitely a good suggestion. I think that's probably what we have to do. We have to make some selection already here. We did some selection of maybe only training 42 languages, and this 972 language model I actually trained for 3 months. So it's definitely something that is not that scalable, and we don't have the resources as Google has in that sense either. But selection is something we will also, we will probably do that. We can discuss more details later also. If you have any suggestions, are really welcome here. So I'm basically here now without any further big ideas. So I'm looking for suggestions like this one.
Maybe one more quick question. At the beginning, you map the sentence to some sentence representation, which is typically a fixed length vector, I suppose. I can feel some bias towards the difference between short and long sentences implies that there is different ratio of compression. So is that a problem or not? Because in addition, different languages tend to have long or short sentences.
Yeah, no, so the way of mapping everything on a fixed length vector is not the way that we should go. So this is just a practical way of handling this NLI classifier right now. So I would at least would have that sequence that we have, for example, that we have in neural machine translation, that we have access to all these different points in the sequence, just because we have different amounts of information that we want to capture, and having the same kind of vector representing all kinds of differences also inside of the same language is not possible. So I guess we need this kind of more structured representation of a sentence, also in the vector space. So it's not going to be just one vector, but it's going to be a sequence of vectors, or maybe a tree of vectors. I don't know what yet. So something.
Oh, I see.
Yeah.
Thank you. Any more questions, please?
Have you considered using Babelnet to augment your data?
No, I haven't, not yet. I should do that, especially because we have one member of the Babelnet team now in our team, so I should definitely do that. Yes, no, it would be great suggestions again. So yes, we should do that. In what way should we do that?
No idea. I just got to know Babelnet a little bit, and it sounded very similar to what you do, only that it's just concepts. I didn't even know, sorry, that you were part of the consortium.
No, I'm not. So we have someone from Babelnet in our team now. There. So definitely we have to think about different data sets that we can make use of, and there's many similar projects also running that try to find these kinds of conceptual spaces. I think we have to talk to many other projects as well, and to follow, of course, closely what they present and publish. And I guess that here's also a lot of the similar ideas going on. So yeah, that's one reason for being here and also discussing with you. And yeah, no, so I hope we can build some kind of network of common interests. That's also part of that project, of course, to find out connections. Also with other projects that focus on, as Jan is pointing out, these symbolic representations that hold across languages. So I mean, those things are interesting as well for us. Yeah.
Do we have any more questions? Not really. So thank you again for accepting our invitation, and I hope we'll hear about your results later.
Yes. Thank you.